Is that actually allowed in the license now? I don't know. I don't know. They did change the license? Nonetheless, I have absolutely no intention of starting a business selling benchies, so that's not what we're here for today. We've been sold on the idea that 3D printing is for prototyping, and that is absolutely true, but there are huge benefits to almost immediately seeing the results of your design decisions and to test them in real materials, like plastic. But to get to the point, we've been unsold on the idea that 3D printing is for final manufactured products, and that is compounded by the vast array of trinkets and useless bits of non-functional tat that we see not only every day on social media, but also it's all over all the STL sharing sites. I think we need to challenge that. I'm not saying there's anything wrong with it, but we need to challenge that as being the only thing you can do with a 3D printer. And so today I'm going to leave the house and ask someone who knows. I know, right? Let's go. This video is sponsored by Phaetus, and I've got a couple of new products to show you. They really are cool. You don't want to miss that. More about that later. This is Mark. Mark works for a company called Endoscope Eye.
So I'm the design engineer for a medical innovations product company, and we started out in 2012 with a little gimmick for connecting smartphones to medical endoscopes.
Which doesn't immediately sound like it would be associated with 3D printing at all, and that, I think, is what makes this interesting.
I'm a senior lecturer in mechanical engineering, and I've been teaching CAD, CAM, FEA, and CFD since, well, for 20 years now.
I do know Mark personally. That might be surprising, as he's all those things he's just mentioned, and I'm, well...
2005,
I don't think anyone's going to fact check it.
No.
Well, you never know.
Yeah.
But that's why I asked Mark for an interview. He's got that intersection of knowledge between scary business world and actually teaching stuff. His designs are also unsurprisingly pretty good. Anyway, my aim today is to try to get more insight into how you can really sell a printed product directly as an actual product rather than just as kind of like handcrafted things, if that makes sense, and why you might find it's even a better option in some ways. The first question you might ask of any business that's mass producing something like this is, why are you using a print farm? Because you've obviously got some scale there. Why not just get them made using injection molding, which is the usual way to manufacture things? And that is exactly what I asked first.
So we began with the traditional manufacturing method. So I'd do the design, I'd refine it, I'd iterate it. And then once we were happy with the form, fit and function, we would then prototype it, get it ready for injection molding, send off, commission the tool, and initially, because this was back in 2012, it was more cost effective to produce it in China. And that introduced a few challenges that you'd expect, such as communication and also delays in revisions, but also delays in getting hold of the parts. This is, as you can imagine, was quite an expensive process. Tooling can be anywhere between £15,000 and £20,000. So you kind of have to amortize the cost or spread that cost of that investment across the products that you make, which means you kind of have to place a bet on how big your market is. I think it was around about 6 months after the initial design had been finalized, we managed to get it manufactured and got it out on sale, by which time the next generation of smartphone had been released.
Why did you go down that route in the first place? When you were effectively starting a business scaling up, you could have started with FDM parts. Was it the legitimacy concerns or something else?
Back in 2012, our initial prototypes were all made through SLA. We mainly used SLA at the time because of the fidelity. We could get fantastic fidelity. We could see exactly how the part would come out through injection molding, but the material properties weren't there.
By that, do you mean brittleness?
The parts were brittle, geometrically great, or they were way too stiff, so they wouldn't give you any kind of compliance, and when they failed badly. But there was a bigger issue, and that was SLA materials typically use a wide range of sensitizers to stop the entire vat of resin curing under the laser action. And those stabilizers are very aggressive when it comes to the skin. You can get very sensitive skin conditions.
So the deal is this. Mark started out thinking that FDM was some kind of inferior manufacturing method. That's kind of what we all think, as I said at the beginning of the video, because, well, that is the $64,000 injection mold die question, isn't it?
Just to make the point that when you started that many years ago, there would have been 2 iPhone releases a year at most.
It was one every 2 years.
It was one every 2 years.
Yeah,
so
yeah.
you could make an adapter, get it tooled, injection molded, and know that you could stick with that adapter effectively for up to 2 years or more. And then if you look at now, I don't really know how many.
Yeah, it's typically 4. They have a range of 4, and it's on a biannual basis. Every couple of years, they'll come up with a new variant. But yes, this can be changeable. In fact, we can often be surprised. We have no inside information on the new devices that are coming out. We follow the media like everybody else. So now we currently have a product portfolio of around about 36.
Of those 36 adapters, some parts, and this is the point, this is why you're getting these parts injection molded, some of those parts are the same across all the 36.
Absolutely. They're common across the entire range.
So this is what I found surprising, but if you think about it, it makes sense. You've got a relatively small company here that's having to adapt quickly to new phones coming out at a rate that's almost as fast, or in some cases faster, than the speed it would take to have the products made for them. And as Apple speeds up, it's easy to see that that becomes a problem pretty quickly. That can only be solved with, well, a faster manufacturing method. Or, of course, spending more money getting things done faster with injection molding. But the point is, the faster manufacturing method can be 3D printing. That's a good point to segue into the practical aspects of making a design fit for the consumer when you are 3D printing rather than getting something made by someone else.
It's different. There are dominating factors when you're injection molding. Everything has to be orientated within the tool. You need to think of cores that may need to be removed in order to get voids from the part. I mean, a key example would be the locking ring. So the locking ring, it looks beautifully simple. However, in order to injection mold this, is really quite tricky. We have to have a hydraulic removable core, so it unscrews from the tool before you can release it from the tool. It's got draft angle, so it comes off the A side of the tool, but the inside, it's got these lovely big threads on the inside, so it's biting into the tool.
It sounds to me a little bit like it's actually easier to design things for FDM.
In many respects, it is. The mating part for that is very easy to print on FDM. And I have printed these before. And yeah, they work fine. They work fine up to a point.
I think the takeaway from that is that the FDM version of this material is not in any way inferior. In fact, it actually works to your advantage. So that kind of dispels a bit of the myth that FDM can't be necessarily used as a final product, because it doesn't seem to be much of a problem from the material standpoint. Quite the contrary. And in terms of actually designing for FDM, there's some fundamental differences in not only whether you're willing to consider that, but also really how you go about the design from the ground up.
I had a personal resistance against using additive manufacture for anything other than early concepts, prototypes. It was a conversation with one of my colleagues that made me change my mind. Again, I was going through my usual process. We were about to release the iPhone 14 and the 14 Pro, and the 14 Plus, and the 14 Pro Max. We were developing those prototypes. I was handing them over, and my colleagues said to me, well, why can't we just send these out? These are great.
So this was ultimately a case of someone who's outside of the 3D printing environment looking at the product and saying, this is actually fine, whereas you'd previously had sort of biases to make you think that it wasn't.
Yeah.
That's fair to say.
I was carrying a lot of luggage.
Yeah.
And the part had been designed not for FDM, which
Yeah.
was a big differentiator. We were making the parts at the time. We'd moved away from injection molding, having them made through SLS. SLS was proving problematic. The parts were coming out warped, and some of the finer details, such as the screw threads you mentioned, we were getting a lot of trouble getting clear valleys, clear peaks or sharp peaks on the threads, which are essential to holding your components together. And so we were getting a wastage of between 50 and 60%. We were losing 50 to 60% of our parts.
So you're actually throwing away 1 in 2 adapters.
Yes.
That was coming off the production line when you were having them commercially made.
Correct. Yeah. We worked so closely with our subcontractor to try and get that resolved. All the things we did. And at the end of the day, it was going to be, well, we just can't produce those. Maybe you should injection mold them. I started looking at other ways I could put the part together. And it was during that process that I thought, well, what if I looked at a different way of putting the FDM parts together? Maybe I could overcome some of the issues that were mentally blocking me from trying FDM, such as the need for lots of supports for big flat areas and things like that.
And this is how you get to why the recent iterations of the adapter are designed how they are. When you switch from thinking maybe we could print this design out in FDM that we already have to maybe I can design this to be printed in FDM, those two thought processes sound the same, but it does subtly shift the focus of the design process a bit.
If I'd printed it vertically or looked toward printing it vertically, I would still have witness marks on the inside edges, which would be contacting the edges of the phone, which would change the way that it fit or change the quality of fit on the device. And it would also add witness marks to our threaded features, which we were trying to fix in the SLS models.
And just to clarify, witness marks are, in this context, will be areas where support's been removed.
That's right, yeah.
Yeah.
So and witness marks, to my mind, are a necessary evil, but they can be minimized through design. I boiled it down into the functional surfaces, the surfaces that we needed, the surfaces that I needed a good finish on, and the surfaces which were less important aesthetically. When I looked at the aesthetic surfaces that were not printable or not really that required, I looked at ways of hiding them. So I had to get a bit creative in the way the part is divided into those parts. But realistically, it's something you can do for any product. If you have large empty voids that you would otherwise have to fill with supports, do you necessarily have to have it as a large empty void, or can you separate the top and so you're just printing walls? Ultimately, it's down to you as the designer to design for the process. And that's the exercise I went through. And it was not a quick process. There's two elements to that. One is the design knowledge and the other is the materials knowledge. You need to know how the material will want to move and the way the material will not want to move and the way you can design sympathetically for that. So again, this is a reason why I don't run the printers to their maximum, because I don't want to introduce any risk of variations in line width. I don't want any kind of variation in product porosity or density. I want to know I'm well within the limits of the printer and the material that I'm pushing through the nozzle. Once I've got that stable, I've got a very stable platform to build on. I know that whatever comes off the printer will be absolutely fine, providing the printer's behaving itself. Again, this is a reason when I finally unloaded my baggage and started working towards more production-ready machines, I then felt much more comfortable that when I turned out a prototype for my colleagues to try, that I could do that more than once, and it wasn't necessarily a Tuesday.
So the way to avoid that is to have all the hardware ultimately the same.
Yeah. Again, that is partly pragmatic, but it's also required by regulation. Each of these products is produced in a known way, from a known material batch, which I can trace back to the manufacturer. I know which machine it was printed on, what date, which print in that day it was, and I can trace a product that goes out to the customer. So if there's any issues that they may have, I can trace it right the way back to the raw material.
I want to show you this. This is the sponsor segment for the video, but it's also 2 cool new products, so keep watching. This is actually what Phaetus are calling a cool build plate, and not just because it looks cool, but because you can save heat and therefore energy by printing using this build plate over a standard PEI sheet. Normally, as they say, you want 65 degrees C for PLA, and I actually personally use 70 because it seems to perform better with PEI. The difference between even 50 and 70 degrees C is more than you think when it comes to energy cost over time, for reasons I don't want to go into. And indeed, you'll see that if you use 90 or 100 for ABS as a bed temperature, you will notice it uses a lot more energy, as well as the extra time it takes to heat up. And that is because it's significantly further away from ambient temperature, so the losses are relative to the ambient temperature differences. But I did say I wasn't going to talk about that. But there's extra reasons to use this build plate, because the coating is such that the bed's grip is more like it used to be in the old days when we used build tack, but it also releases like a PEI sheet when it cools down, so it's getting much closer to a best of both worlds situation. I made a short to show you how this is achieved, and this is some of the footage from that, but the TLDR is that the manufacturing method is creating a lot of surface area that uses tiny microscopic level bonds to hold the parts. And we can see that extra surface area under macro. When the surface cools, it presumably shrinks differently to the material that's printed on it, and that is causing them to separate from each other in the same way as PEI. And you could see the difference between PEI and the Conweb build plate when you get really close up. The other thing I wanted to show you is the Phaetus Conch A1 and A1 Mini hot end for the Bamboo A1 and A1 Mini, obviously. It's a straight swap interchange to these. They're way easier to change nozzle than other printers. There's 2 versions with 2 different coatings. I have the Plus, and I've been printing with it since I fitted it in, I think, around May. So it's been used for all the videos I've made since then. You can check out both of these new products or any of the Phaetus stuff using the links below, and also if you have a K1 variant, maybe go and check out the DXC pictured extruder. Thank you, Phaetus, for sponsoring this video, and back to it. And finally, I want to show you something that Mark's doing that I haven't seen anywhere else, and it seems like something that I could actually base a future episode on and maybe expand upon and see where we go. So listen up to this, because it's really cool. It might not seem like anything unusual at face value, but it's a different take on the standard support and interface system that slicers do already use, and instead it's taking that into design time. But at the same time, it wouldn't necessarily have to be taken into design time. You could, in theory, integrate this into slicers, I think, in some way.
These are my support regions. These will be seen, and so they're produced quite neat and quite straightforward. So I've designed out any need for support there. But unfortunately, we have this cantilevered region here. If I had standard supports, we'd have an irregular pattern around here. We'd have some little ups and downs in the bottom surface here.
And you did used to have standard supports for that, didn't you, until very recently?
Yeah. And when we came to remove them, sometimes they'd be biting really hard in some points, and then I'd need to get a knife to cut them away. And in other regions, I'd have to break them away, or they just wouldn't be touching. And so it meant I had to introduce a larger clearance between parallel faces. So what I've done is I've created these consistent geometries that are part of the main part with a slight chamfer at the interface. So the part, or these little ribs are wider than the line width. They're usually a couple of line widths, and with a chamfer at the bottom so that there's a clean breakaway edge so that they will come away the same every time.
So I hope this has been an interesting look into a side of FDM that I don't normally look at so closely from in the studio for obvious reasons. I think there was stuff to take away that could be implemented into any design, whatever it's going to be used for. I appreciate Mark taking time out of his day to explain a lot of this to us, and let me know whether you found it useful, as always, in the comments below. I will see you next time where, depending on when this gets released, we may or may not be talking about wet filament again, because apparently that is a hard topic to truly understand. Thank you for watching.
Cool.
Yeah.
And that would be ready to go up someone's nose
Pretty much.
or ear.
In their ear, yeah, up their
Yeah.
nose, yeah, all the rest.